Yeah, thanks everyone for coming. I'm Steven, and today I'm with my joint first author Yinlin, and we're very happy to present our work titled Top Leaderboard Ranking Equals Top Coding Proficiency Always, EvoEval, Evolving Coding Benchmarks via Large Language Models. So to start with some background information, large language models have been widely adopted for a wide range of different coding tasks. And we've seen large language models be a very key part of many of the recent developments in AI-based coding tools such as GitHub Copilot, which has generated more than 3 billion lines of accepted code. And many of these tools work by leveraging the powerful code synthesis ability of these large language models in order to turn natural language descriptions provided by the users into code. And this is exactly the task of code synthesis, where state-of-the-art large language models have become the default solution. However, how do we evaluate the code synthesis performance of these large language models? While researchers have constructed handcrafted benchmarks like EvoEval from OpenAI or MBPP from Google in order to measure exactly this. And typically, these benchmarks provides an input prompt to the model, which consists of the function header, as well as the docstring in order to describe the intent of the function. And provided with this input, the large language model will then auto-complete the function body. And finally, these benchmarks will contain test cases, which, and different from natural language tasks, for coding tasks, we can actually directly execute the generated code against these test cases to measure the functional correctness of the large language model generated code. Furthermore, recent works like Eval Plus has also added additional tests in order to produce EvoEval Plus or MBBB Plus in order to increase the robustness of the evaluation framework. However, existing benchmarks, while very good, have the following limitations. First, they're limited in their amount and variety of problems. So for example, the popular EvoEval benchmarks only consist of 164 problems that are self-contained functions, which lack variety in terms of both problem type, but also domains. As such, it can be insufficient to fully measure the complete code synthesis capabilities of large language models. Second, existing benchmarks are also very prone to data leakage. For example, many of the popular benchmarks have been released almost 4 years ago, where leaked solutions can also be found on third-party web pages. And furthermore, there are even recent works which show that there are substantial overlaps between the benchmark solutions as well as some of the open source training corpuses. So while recent large language models have been climbing the leaderboard by achieving higher and higher pass-1 scores, often with only very slight improvements, in this paper we asked, is the leaderboard performance really reliable and comprehensive enough to measure the program synthesis abilities of large language models? So in order to address these limitations, we propose EvoEval, which is a new set of program synthesis benchmarks created through evolving existing problems. So EvoEval transforms the existing problems into multiple different targeted domains. So we include 5 different semantically altering targeted domains to make the problems either more difficult, more creative, applying subtle changes to the problem, combining multiple problems together, and even creating tool usage problems. Furthermore, we also construct 2 semantically preserving domains in order to make the problems either more verbose or also more concise. In total, we produce more than 800 different problems across our 7 benchmarks for a more comprehensive evaluation of large language models. So now I'll briefly describe the transformation approach we do in order to produce new problems in EvoEval. So we begin with the original problem. In this case, we want to transform it into a more creative problem. So we start by using GPT-4 with our transformation prompts in order to get our initial evolve problem. We then generate the test cases as well as the possible solution. However, initially the evolve problems produced by the large language model may include small inconsistencies like incorrect examples. So as such, we then instruct the large language model to refine the problem by adding or fixing example test cases in the docstring through using the generated test. And then of course we regenerate the solution. We then check if the new solution on the test input will produce the same output as the previous solution. So the intuition we have here is that since the refined problem should only include minimum changes, the solution output should then remain the same in the absence of any inconsistencies. So if there are any differences, we ask the large language model to further revise and fix any inconsistencies and repeat the process. If both solutions agree on the outputs, we perform final manual inspection in order to ensure that each problem and ground truth solutions are correctly implemented. In the end, we produce our data sets, which consist of not only the evolved problem, but also the ground truth solutions, as well as any test cases to evaluate the functional correctness. So using this pipeline, as well as the seed problems from EvoEval, we produced 828 problems across our 7 different benchmarks. In particular, as mentioned before, we defined 2 different types of transformation problems into semantic altering ones that changes the semantic meaning of the problem to make it more difficult, more creative, apply subtle changes, combining multiple problems together, as well as 2 usage problems. Furthermore, we also include our 2 semantically preserving datasets that only modifies the description to be either more verbose or more concise, but keeping the same semantic meaning. Using EvoEval, we conduct a very extensive study using 57 different large language models, including both closed source and open source ones, and measure the functional correctness. Now I'll pass it on to Yinlin to talk about some of the results.
Okay, so now we move on to the results. So this table here shows the pass at 1 performance and the ranking of selected large language models. We can observe that compared to the high success rates obtained on standard benchmarks like EvoEval, there is a significant performance drop when evaluated on EvoEval, our new benchmark. For example, GPT-4o, which achieves over 80% pass rate on EvoEval Plus, falls below 55% when evaluated on EvoEval difficult benchmark. This shows that EvoEval constructs more complex and challenging benchmarks for code synthesis. Furthermore, this performance drop is non-uniform across models, leading to significant ranking changes in the leaderboard. Interestingly, despite we use GPT-4 to create the benchmark, it does not rank the highest on our leaderboard. So next, we plot the detailed EvoEval Plus scores versus the EvoEval scores across models. We can observe that the shaded region shows a large portion of the large language model tend to be worse on EvoEval compared to EvoEval Plus. Meanwhile, some language models have a much higher EvoEval Plus scores compared to their EvoEval performance, highlighted as the blue shaded region. This implies potential data leakage issues of popular benchmarks. So next, we present more detailed analysis on our individual benchmarks. We first focus on verbose and concise, where we simply rephrase the problem description in a more descriptive or concise manner without changing their semantic meaning. So this figure displays the original EvoEval scores as bars and the performance changes as arrows. We can observe that instruction following large language models, they tend to generally drop in performance when evaluated on this verbose or concise compared to the original EvoEval. And this is drastically different from their base variants, where we can even observe performance improvements. So similar patterns are also observed on the semantic altering benchmarks such as Subtle, where we apply small semantic changes to the original EvoEval problem. So this finding suggests that although the instruction-tuned large language models are expected to align better with instructions, they're actually more sensitive to this rephrasing or subtle changes in problem description, and this might also indicate potential benchmark memorization or contamination problems. So due to time limits, we will only show one of our semantic altering benchmarks. The ability to combine different known concepts to solve new problems is crucial for code synthesis, especially when we want to solve complex tasks. So here we take a deeper look at the combined benchmark. Recall that each combined problem is created from combining 2 parent problems from EvoEval. Here we measure the compositional percentage, which means like how often a large language model can solve a combined problem when it already solves both parent problems successfully. So the result is quite surprising. Take GPT-4o, for example. For 38% of the time, it is able to solve 2 parent problems individually, but failed to solve the combined problem. So this shows that while current state-of-the-art models perform well on simple coding tasks, they still struggle when they need to incorporate these known concepts into more complex solutions. So to conclude, we present EvoEval, an evaluation framework that creates a set of new benchmarks by evolving existing problems into different domains, in order to have a holistic and comprehensive evaluation on the code synthesis ability of large language models. Our evaluation on 57 large language models showed drastic performance degradation on EvoEval, and additionally, we observed significant ranking changes compared to prior leaderboards, indicating potential overfitting on existing benchmarks. We also provide additional insights, including the breakness of instruction following large language models, as well as the limited compositional generalization abilities of models. In future work, we hope to apply our transformation framework to develop more realistic and challenging benchmarks, and to incorporate ensemble or specialized large language models for benchmark construction. Feel free to check our poster right after this talk for more discussion, and feel free to check our papers and websites for more details on how to use the benchmark. Thank you. We're happy to take questions.